Welcome to in-class activity 2A. In this activity, we are going to model the trajectory of the Ferris wheel using trigonometric functions. Imagine riding on a Ferris wheel that is rotating at a constant rate. Consider two distances, x, your distance to the right of the vertical line through the center of the wheel, and y, your distance above the horizontal line through the center. The question is, what is the value of y when x is at its greatest value? What is the value of x when y is greatest? Are x and y ever equal? I want you to pause this video, think about the question, provide some answers, and we will try to take it together. Your answers to these questions may vary, but let's consider a possible answer. On the right, let's assume that this is the path of the Ferris wheel. We have a horizontal line passing through the middle and a vertical line above. Now, this is the vertical line that we want to consider above it, and that to the right is the x that we want to consider. If we assume that we are starting from somewhere here and going up, then on this circle, we may get different x's and different y's. For example, let's assume when we are here, we are going to get some y1 and then some x1. But the question is, what is y when x is at its greatest value? Now, x is going to be at its greatest value at this point. This is the point where x is going to be at its greatest value. And so here, there is not going to be any y because x is here. Y is going to be 0. Y is also going to be at its greatest value at that end, the maximum point. And at that point, there will be no x when y is greater. So x is going to be 0 there. Now, the second part of the question says, are x and y ever equal? Are x and y ever equal? Now, as we travel, right, at a certain point here, when we are midway between, remember that this is about 90 degrees. And so when we are midway between, we can get some y value and then some x value. Now, if this is 90 degrees, then when we are midway between, we are going to get an angle of 45 degrees here. And when this is 45, the top also is 45. And so yx, this is 45, and that is 45. The only way this angle is going to be the same as that angle is when x and y are the same. All right. And so the question is, the value of x and y are equal when you are halfway from the middle to the top. All right. When you are halfway from the middle to the top. The objectives for the activity. In this activity, you will understand that sinusoidal functions can be represented by motion along a circle. You will be able to graph the horizontal and vertical coordinates of a point as they move around a circle. And you will be able to interpret circle diagrams in the context of a model. Suppose that a Ferris wheel rotates counterclockwise at a constant rate and takes 24 seconds to make a complete revolution. There is a horizontal platform running along the middle of this Ferris wheel where riders can get on and off. Suppose that you start riding this Ferris wheel at time t equals 0 seconds, starting at the platform in the middle. The question is, part A, when, that is at what value of t, will you reach the top of the Ferris wheel? When will you pass the platform for the first time on your way down? Now, I want you to consider this important words: counterclockwise, constant rate, 24 seconds for a complete revolution. Think about this, pause the video, provide some answers, and then we will try to take it together. Now, consider a circle below here. Now, this is your starting point, and you are going that way. For one complete revolution, when you start here, you go around the circle, come back, and that is going to take you like 24 seconds. When are you going to be at the top here? When are you going to be at the top here? That is like a quarter of the circle. And so 24 seconds divided by 4 will give you 6 seconds. By 6 seconds, you're somewhere there. Now, when you're going to pass the platform for the first time, at that point, that is going to be like half of the revolution. And half of that, and that is like 12 seconds. So at 12 seconds, you are somewhere there. And so if from here to there is 24 seconds, it's 6 seconds, then this is exactly half of it, right? Then that is going to be like 3 seconds. If from here to there, if we are getting 12 seconds here, then half of the 6 seconds is also going to give us 9 here. So you can add 3, 3, 3, 3, 3, 3, 3, 3, and get the other values. Part B. In the diagram, 8 equally spaced positions on the Ferris wheel are marked with points. Plot the vertical positions of each of these points on the axis to the right. The vertical position of each point you plot should match the vertical position of the corresponding point on the circle. On the horizontal axis, label the time value corresponding to each point. The first 2 points are done for you. And so, remember we started from here, we had our 6 there, and between 6 and 0 we have 3, right? And so this is the first point. Remember what we are doing, we are locating the vertical positions with respect to the time and then the rotation. So at 3, we are somewhere there. So do the rest, pause the video, try your hands at it, and then we will take it together. Now, if you remember, we had our 0 here. This was 3. The topmost is 6. This is 9, 12. We have 12 plus 3 is 15. That is 18. That is 21. For one complete revolution, we come back to 24. And so it is going to follow the same pattern. At 0.0, we are here. That is our starting point. When we move to 3, we are somewhere there. Just draw some horizontal lines, right? And then at 6, we are at the topmost position. Now at 9, we come down a little, but that point corresponds with 3. So 9, we are here. At 12, we are passing the middle for the first time. So we are at the same point as 0. At 15, look at it, we are descending down a little. So at 15, we are at this point, because this point is going to correspond with that point. And at 18, we descend down at the minimum point. Then at 21, we rise from 18 to 21. And then at 24, we come back, right? At 24, we come back. And so that is how our points are going to look like. Now draw a smooth curve through the points we plotted in part A. What do you notice? I want you to pause the video, do this and let's take it together. And so what we have done here is that we have just joined these lines with a smooth curve. And that is what you see here. Now the next question is, what do you notice? We notice that the graph appears sinusoidal. Now consider your horizontal position measured from the vertical line through the middle of the Ferris wheel. So we are considering that our horizontal position is measured through the middle in the vertical position. The diagram shows 8 equally spaced points. So these are the 8 equally spaced points, like we did in the first one. On the Ferris wheel, on the axis to the right, plot your horizontal positions versus time as the Ferris wheel rotates counterclockwise. Points to the right of the center corresponds to positive values, while points to the left of the center corresponds to negative values. Label the t values on the horizontal axis corresponding to each point. The starting point corresponding to t equals 0 is plotted for you. Once you have plotted all points, draw a smooth curve passing through each of them. Please think about this, pause the video, try your hands, and let's meet to take it. Remember what we are doing. We want to plot the horizontal positions versus time as the Ferris wheel rotates counterclockwise. So we are still going this way. Now I want you to think of this as determining the position of a rider's shadow if the sun is directly above the rider, so that the shadow is directly below the rider. And so think of this as you have a rider and you have the sun, right, directly above him or her, and you want to determine the rider's shadow. And the shadow is going to be below the rider. If you remember that initially we were somewhere here, this is at the top. And so as we move up this way, this begins to move down. As we move up this way, this position begins to move down. And so as you can see, this is what we are getting. So at point 3, this is where we are. Now, as we move right to the top, when we're looking for the vertical position, this gives us 6. And so at that point, we are coming to this point. And then as we pass here to that point, you will see that we begin to also come down, right? And then as we reach that point, we descend exactly to this point, to the lowest point. As we continue to move on, this rises. And as we get here, we are now somewhere there. And as we continue to rise, we are rising, and eventually we come back. So that is going to be the nature of our graph. Now, consider the curves that you plotted in question 2 and 3. A transformation that takes you from one of the graphs to the other is called a phase shift. In this case, the phase shift is 6 seconds. Explain why the word shift is an appropriate way to describe this transformation. And so for the first one, when we were looking for the vertical positions, this is what we had. And then when we were looking for the horizontal positions, that is what we have. Now this graph has been shifted, so explain why the word shift is an appropriate way to describe the transformation. Pause the video, think of an answer, try your hands at it, and we will discuss it together. Remember that what we want to do is to explain why the word shift is appropriate. If you look at the first graph, we are starting from here. And the second graph, that is where we are starting. If I want to bring this second graph on here, then the only position that I can move it is to this position, because it is starting at the top there, and this is the top. The first top that we can encounter is here. So we can start this graph from here, right? And so this is what that graph looks like. Now you can see that the starting point has shifted 6 seconds for that. And this makes it appropriate to use the word shift. So we can say this one has shifted to the right by 6 seconds, or that one has shifted to the left by 6 seconds. Now consider the curves that you've graphed in question 2 and 3. A transformation that takes you from one of the graphs to the other is called a phase shift. In this case, the phase shift is 6 seconds. Explain what the quantity 6 seconds has to do with this transformation. And so this is what we discussed in the earlier slide, right? The second function is 6 seconds ahead of the first function. Or you can say that the first function is 6 seconds behind the second function. Write 1 or 2 complete sentences explaining how circles and sinusoidal functions are related. I want you to pause the video and try your hands at it, and we will take it together. Now your answers to this question are going to vary, but sample answers are that if you travel around a circle and keep track of how high up you are and plot these points on a graph, you get a sinusoid. So when we looked at the vertical positions, we got a sinusoid. Or you can say that as you go around a circle, both the horizontal displacement and the vertical displacement change according to sinusoidal functions. Now, as an example, if you look at what is up here, you can see how for each angle, we use the y value of the point on the circle to determine the output value of a sine function. And we'll be looking at this in details as we progress in the course.